Hello everybody. Welcome to the multi-arm bandit video in the large-scale machine learning section of ML Expert. I highly recommend that you go ahead and look at the frequentist and Bayesian A/B testing videos. So in the similar way that we've talked about before, we can have an experiment where we have some control experience and we have some treatment experience. The control experience could be that we're sending out push notifications which recommend that users look at the top posts of a particular app. Now for the treatment group, we hypothesize that sending push notifications, which recommend personalized posts, will have a higher probability of being clicked on. Now in our last videos, we talked about how you would typically divide your audience in half, and half of them would be in the control and half of them would be in the treatment group. The problem is, what if the treatment that we're experimenting with is absolutely horrible? And now we're stuck with 50% of our users potentially getting a horrible experience for 2 weeks. Now, obviously you can cut experiments short, but generally it's still a problem that a lot of your customers are still getting a horrible experience. One way to try to mitigate this would be assigning 99% of your customers to the control group and only assigning 1% of your customers to this treatment in an effort to offset the impact if the treatment experience happens to be really bad. As we talked about in the last videos, though, it doesn't really matter if we assign 50% or 1%, the same number of users will likely have to go through the experiment in order for the experiment to be measured correctly. So that's not really a great way to mitigate the potential of a terrible treatment. So what we really want to do is we want to minimize the negative business impacts while still experimenting at a reasonable pace. Let's say that we're into an experiment for 2 days. So we expect to run the experiment for 14 days, and so far we've measured that control has a 7% click-through probability, and the treatment group has a 5% click-through probability. Now, let's say that we ran the experiment for the full 14 days, and these happen to be the ending click-through probabilities for each treatment after those 14 days. Well, in this case, it's better to route all of your customers all of the time to the control experience because the click-through probability now is higher, and eventually it will be higher. But again, we don't know 2 days in that it will be eventually higher. Now, on the other hand, it's possible that we are measuring 7% and 5% for the click-through probabilities 2 days into the experiment. However, if we extended that experiment to the full 14 days, this could, in fact, be the final click-through probability, and this could be the final click-through probability for the treatment group. The problem now is that if we did just route everyone to the control group after just 2 out of the 14 days, we would miss out on an eventual 2% gain if we had explored the treatment option a little bit more. So really what we're asking here is how should we trade off exploration versus exploitation? So we could explore the less promising treatment but miss a potentially better control. Or we could exploit the potentially better control but miss an eventually better treatment. So a very simple way to handle this would be using what's called the epsilon greedy strategy. All this means is that if we measure in an experiment, say 2 days in, we'll simply route each customer to the better performing experience with the probability of 1 minus epsilon, and we'll route people to the less performant experience epsilon % of the time. So in this case, any individual user here would have a 90% chance of being routed to what we measure to be the better performing experience so far, and they would have a 10% chance of being routed to the worst performing experience so far in an effort to mainly exploit this higher click-through probability, but also in an effort to explore this treatment here such that with more samples taken would actually outperform the currently best performing experience. So let's say that we follow this pattern here, and we've now assigned all of these customers to some particular group. And now what we've measured is that the control experience with more samples actually fell to 6%, and the treatment group actually increased the performance to 7% click-through probability based on all of the samples that we now have. So we would simply flip the probabilities of getting the control and treatment. So now, since the treatment experience performs better than the control experience, we would route 90% of the traffic to the treatment and 10% of the traffic to control in order to explore this a little bit more in case that we get more samples and it actually ends up performing better than the treatment. So one question we can ask now is how much better is this epsilon greedy strategy over the random allocation, which is just A/B testing? Well, we have to first understand something called reward. Reward is the outcome of allocating a user to a particular experience. The experiences here are either A or B. Now, the total reward obtained by a multi-armed bandit, and here the arms in the multi-armed bandit, are just the different treatment groups. So for A/B testing, we had the A group and the B group, and here those A and B groups would just be referred to as arms. So the total reward obtained by a multi-armed bandit is the sum of the rewards obtained by allocating some user U to some arm A. So here, mathematically, that's how we would express this. We would sum up for every single user all of the rewards that a particular arm gives some user. The expected reward is just the average reward given by some arm to some user. So now that we understand reward, we'll talk about regret. Regret is the reward obtained from the optimal arm minus the reward obtained from the arm that we actually chose. So if we have a user and we assign them to the best possible arm, then there is no regret. And in general, we'd like to minimize the regret. So if you recall, here is the reward, and the regret is just the optimal arm, here indicated by A star, minus whatever we chose to give those users on average. This equation here is the expected regret. So in general, the expected regret of A/B testing is the number of users times the difference of picking the optimal arm and whatever arm that we picked. Now for epsilon greedy, it's mostly the same thing. The only difference is we will have a fraction of the regret because some fraction of the users will actually be sent to the optimal arm over the suboptimal arm. Now the problem with both of these is that they're both linear in regret. So the expected regret increases linearly with the number of users that we introduce into the experiment. Thompson sampling is a technique we can use to get a logarithmic regret as the number of users grow. This is a very important distinction here. What this means is that for every user that comes into our experiment, each subsequent user will experience less and less regret. That's what makes this different between the other two techniques. So what is Thompson sampling? Well, it's based on a very simple idea. All it says is that the frequency that a user should be allocated to some arm or experience, that should equal the probability of that experience being optimal. So if we had two arms, let's say we have control and a treatment arm, and this control arm had a 30% chance of being the best arm, and the treatment arm had a 70% chance of being the best, then Thompson sampling says that 30% of the users should go to control and 70% of them should go to treatment. Now, as we assign different users to different controls and different treatments, the chance of each arm could change, and so will the allocation probabilities of each user. So the next natural question is, what does that best mean? So how do we know what the probability of being optimal is? So let's say that we have two groups again, and how we represent these click-through probabilities. So here, this is a click-through probability of 6%, 7%, 8%. What we do is we start with a beta distribution where alpha is 1 and beta is 1. What this means is that we have a completely uninformative prior about the click-through probabilities for both of the arms. Feel free to visit the Bayesian A/B testing video, which covers the beta distribution. Now, as users come in, so let's say we pick this user, and let's say that this push notification that we sent out, the user does in fact click on it. What that means is that the beta distribution is now updated to include that one success. Here, that success means that for this particular A arm, we sent out this push notification and the user clicked it. Let's say we assign another user here to arm B and they do not click the push notification. then that would also be reflected in the beta distribution parameters. And these lines just visualize the beta distribution. Now, as we continue and sample more of our population, these beta distributions will be updated for each time that a user does or does not click on the particular push notification generated by that arm. Eventually, the beta distributions will take this shape based on the number of push notifications clicked per arm. So how we determine the probability that this arm is better than this arm or this arm is better than that arm is by just sampling each of the arms. So we will sample this beta distribution, say 100 times, and we'll sample this beta distribution 100 times. And the percent of the time that these samples are higher than these samples will equal the probability that this distribution is greater than this one. So that's how we know the probability of some particular arm being optimal. So during these multi-armed bandit experiments, how do we know when to stop? We stop when there's a 95% chance that the value remaining in the experiment is less than 1%. How do we measure that? Well, let's take our beta distributions that we had from our arms earlier, and we start by sampling these distributions. So here, let's say we have 100 samples of this distribution and 100 samples of this distribution. We then count how many times this distribution is greater than this distribution. So here, 58 out of the 100 samples that we took from this distribution were higher than this one. That leaves 42 out of 100 samples here. This again is the probability of being best. Now going back to the actual samples, what we do is we take the max sample across all the arms. So somewhere in here, this arm generated a 9.2% sample. So then with this 9.2, we take the optimal arm, which in this case was this arm because it got a 58% chance compared to a 42%, and we run this equation, which is the value add equation, for every single sample that we've gotten from this beta distribution. So here we subtract the maximum minus the 7.2 over the 7.2. We repeat this for every single sample in the optimal distribution. Now, if we were to sort all 100 of these value adds that we calculated from these 100 samples, and we were to cut off the bottom 95 of those samples, so here that would be the 95%, if 95 of those samples are less than 1%, then we will stop the experiment. What this means is that there's a 95% chance that the value remaining, or how much value there is left in the experiment, is less than a 1% gain. Both of these are tunable parameters, which you can decide on, but these are pretty common values. All right, so when do we use a multi-armed bandit over an A/B test? Multi-armed bandits are going to be better in cases where we have many arms, as opposed to A/B test, which generally manage fewer arms. Bandits will also move the traffic automatically to the best arm, where A/B test, you would have to manually do that. Bandits are also better for short-term results. So let's say that we were generating the best headline for some news article, or we were generating the best email to send out for a short marketing campaign that would only last a weekend or so. Then you don't want to run an A/B test, because by the time your A/B test has concluded, the campaign or the headline generated for a particular article is no longer relevant. A/B testing focuses on learning, so we really want to know which experience is performing better. Bandits, on the other hand, focus on optimizing, so we're not really focused on learning as much as picking the best treatment in general. And finally, multi-armed bandits generally take longer for the experiment to run, but they do so at the benefit of minimizing regret. A/B testing, however, can take a shorter amount of time, but it won't take into account minimizing the regret. Some practical considerations that we need to think of for multi-armed bandits is how often we want to update the beta distributions. So in our example earlier, it was very fast that we could recognize whether someone clicked on a push notification or did not click on it. That allowed us to adjust the distributions quickly. However, if the customer actions take a long time to record, then that could mean we may not even have a choice of how often we want to update the beta distributions. Thirdly, we have to watch out for non-stationary user preferences. All that means is that user preferences can change over time, and these beta distributions, given enough data, can be rather difficult to adjust, and you could need even greater amounts of data to correctly adjust for some non-stationary preference. Finally, multi-armed bandits can be contextual. So if you hear of contextual bandits, all that means is that the reward associated with giving some user a particular experience depends more on the environment or some context. This could mean what time of day is it, what type of customer is using the interface. It could even be what device the customers are using to interact with your UI. So you have the option of implementing multi-armed bandits yourself, but here are a few tools to help you get started. Optimizely offers multi-armed bandits, Visual Web Optimizer as well, and so does Vopal Wabbit. They offer contextual bandits. That wraps up the multi-armed bandit video in the large-scale machine learning section of ML Expert. Thanks for joining, and we'll see you next time.